So I gave you three spaces: column space, null space, and the row space. So I owe you one more space. So let's look at what's called the left null space. So column space are the linear combinations of the columns of A, span of the columns of A. Row space would be the span of the columns of A transpose, so the rows of A. The null space would be the solution set. Now there is a solution set of A transpose also, and that will be the left null space. But if you think about AX equal to B, I showed you that if X is in the null space, we know by definition that if X is in the null space, that will necessarily go to the zero vector by definition. And if X is not in the null space, as we saw here in my origin vector, X is not in the null space, all such vectors will go to the column space because the component that is in the null space will not contribute to anything. That will just disappear to zero vector. And then there is nothing left in the input space. In Rn, vectors are either in the null space or not. If it is in the null space, it will go to the zero vector. If it is not in the null space, it will go to the column space. So there's nothing left to go to the left null space. So nothing goes to the left null space. So that completes the picture. So I have our matrix, m rows and columns, rank is R, and we have our equation Ax equal to B, which is a mapping. A takes vectors of the type X in Rn because it's got n columns and gives you vectors in Rm. So the input space is in green, Rn. Output space is in red, in Rm. So we have the span of the columns of A, that is a column space, that is in Rm because each vector in the column of A, in a column of A, will have m components, m rows, right? And that is a column. This is also called image or range. Why that is the case, we will see in a minute. But you can kind of see why it's an image. It's a reflection of something that is happening on the left hand side. X is the input, that is the object, and B, the output, that is the image. And range comes from the corresponding nomenclature in the world of functions. Now that was the first space. Remember, it's a subspace, so it's got 0. So this little circle here, that actually refers to the zero vector. Now I had the null space. By definition, null space was collection of all the vectors that will give me Ax equal to 0. So all the vectors in the null space will go to the zero vector on the output side. And the zero vector will, of course, naturally go to 0. And 0 is part of all spaces, so 0 is a part of null space as well. Then I had my row space. All the vectors in the row space will go to the column space because Ax equal to B, if you take a vector in the row space, is the linear combination of columns of A. If it was 0, the vector would be in the null space. If it's not, then that would go to the column space, non-zero element in the columns. But as we saw from our example, row space was the xy plane and null space was the z-axis. A large number of vectors, in fact, most of the vectors in the three-dimensional space were not in the row space nor in the null space. They were linear combinations. Those vectors are linear combinations of vectors from the row space and the null space. They all go to the column space as well. So we have accounted for everything that is happening in Rn. There's nothing that is left to go to the left null space. Now, the row space is also called co-image because column space is the image, and null space is called the kernel. The left null space is called left kernel. Now, let's think about the containing space. The containing space, Rn, on the input side, that is called the domain. That is where you draw the x vectors from. That is like the space where the input vectors live. Similarly, the output vectors, they live in the codomain, that is Rm. So that is the picture. So the arrows are all from left to right, but it's a nice symmetric picture, and it acts much better later on in the very chapter. The very last picture that I'll leave you with is based on this, but it will become symmetric with arrows going from right back to left also. And that symmetry, that elegance, and that beauty of linear algebra is what I want to leave you with, and I'm hoping that will inspire you to learn more about linear algebra and more about mathematics, and maybe do extremely well in computer science. Now, why we have other names? So in order to understand that, let's look at a normal function from R to R. X is in R and the function value is in R elsewhere. And I have the function right there. It's absolute value, the positive value of the square root of x. If I have that, and I can compare it to Ax equal to B, where this mapping is actually from Rn to Rm. The first mapping function is from R to R, but A is from Rn to Rm. Input in Rn, output in Rm. The domain is the space where the argument x lives, and that is just a real number, x number of R. Similarly, the domain is the space where the x vector lives, that is in Rn. Codomain is a space of the output value fx, that is R also in this functional example. But in our linear algebra example, output is in Rm. Range is all possible output values, and that's also called the image. In this particular example, you cannot get negative values, you can get only 0 or positive values. So that is the range or the image. Similarly, in our case, you can get only the column space, then nothing else. No other vector in Rm is accessible by this transformation. There may be other vectors, but not accessible. Co-image is all possible values of the input. In this case, you cannot take a negative value of x because you cannot take the square root. So similarly, in the case of Ax equal to b, row space is considered the co-image. Kernel, if I stretch my analogy a little bit, I can probably define as those values of x that will give me a 0 output value. So x equal to 0 is the kernel. But in the case of a system of linear equations, it's got a more concrete meaning. It's the solution to homogeneous set of equations. That is the null space. Everything that will give me b equal to 0. Co-kernel is the value that cannot be reached in the case of fx. You cannot get output value negative because it's already an absolute value. Similarly, left null space cannot be reached. There is no b that belongs to the left null space. So that's where the names are coming from. Even though I wanted to tell you where the names are coming from and what the names are, we will be using only column space, row space, null space, etc. because all these other names confuse me to be with. But you may need to know it, not from the exam perspective necessarily, but if you look up something on the internet or something, there are people who use those names rather than the names of the spaces like column space, row space, etc. Now, quickly go over the definitions and stuff as a review. Column space is a linear combination of the columns of A, span of the columns of A. It's a subspace of dimension R, where R is the rank is R, m rows and n columns, and the column space lives in Rm because each vector has got m components. Each column of A has got m components, so it lives in Rm. That's the containing space. In order to find the basis for it, you find the pivot column in REF, but don't take it from the REF, go back to the original matrix, and those columns will be the basis. Of course, it being a subspace, it contains the 0 vector. If B is in the column space, we can always find solutions to the system of linear equations Ax equal to B, because we are looking for that particular linear combination, and if we know that B is already a linear combination, we will find it, either one or many such solutions. What I'm trying to say is the column space is a subspace of dimension R in Rm, where R is a rank and m is the number of rows of the matrix A. Null space is a set of solutions to Ax equal to 0. It is the solution set. It lives in Rn because these are vectors that can be x, and the dimensionality is called the nullity or the right nullity, and that is the number of free variables. That would be the number of columns minus the number of linearly independent columns, the rank. So that will be the number of free variables, the columns that don't have pivots. And the basis is a bit hard to find because you have to actually find the solutions, what we call the special solutions. We'll see an example very soon. But the containing space is Rn because each vector x has n components. And so summarizing, null space is a subspace of Rn with dimension n minus r. Now, row space of the same matrix is a set of linear combinations of the rows of A or the columns of A transpose, and that also has dimension R because the number of linearly independent rows of A would be the pivot rows, which will have the number as the pivots, and that is the rank. So in order to find the basis for the row space, you'll have to find the linearly independent rows of the matrix, which would be the pivot rows, either of the matrix or its row reduced forms, because row reduction, elementary row operations do not change the row space. But the containing space is the same as the null space. It's on the input side, Rn. Each row has n elements. So the row space is a subspace of dimension R, rank, in Rn, n being the number of columns. Left null space is the solution set of A transpose Y equal to 0. It lives on the output side, and it's got a dimension of number of rows minus the rank. So this one is not that important, but just to let you know, the left null space is a subspace of Rm on the output side, of dimension m minus r. Now we already saw the connection between null space and row space. They are orthogonal complements of each other. They are both subspaces of the same input space, the domain. They have to be, otherwise they cannot be orthogonal complements. So given the fact that they are orthogonal complements, that will imply that the rank of the matrix, which is the dimension of the row space, plus the nullity, which is the dimension of the null space, will be the same as the dimension of the containing space, or n, so n. So rank plus nullity is n, which is the rank nullity theorem. And we saw that all vectors in the row space are orthogonal to all vectors in the null space. The complement part, which we did not prove, it is there in the textbook. You might want to take a look at it if you're interested. But what it says is this. It says that if I have a vector that is in the null space, I have a vector that is in the null space, and I find a vector that is orthogonal to it, some vector that is orthogonal to it, then that vector that I find necessarily have to be in the row space. It cannot be anywhere else. That is what the complementarity means. It's like the completeness. Similarly, if I have a vector that is in the row space and I find something that is orthogonal to it, that will mean that what I find will have to be there in the null space. It cannot be anywhere else. Again, remember that I gave you xy plane and the z-axis. Those are really orthogonal complements. So if I take the basis for the row space and the null space, together they will form the basis for the input space. Because they are orthogonal complements, the dimensionalities will add up properly. They will kind of cover everything, which is like the xy plane, my row space, and the z-axis. So if I have vectors along the x and along the y directions and the z-axis, then there is a good basis. We also know that all the vectors in the null space will go to 0. The ones that are not in the null space will have to go to some non-zero value, and those are basically in the column space. And we showed you this also. If I add a vector from the null space to a vector in the row space, it doesn't change the right hand side, because a times any vector in the null space will become 0. But remember, most of the input space is neither in the row space nor in the null space in the most general case. Our example, xy plane and z-axis, most of the vectors are neither on the xy plane nor along the z-axis. They were somewhere else. It is important to realize that the union of the row space and the null space would be just a part of the input space. But it's the linear, it's the span of all those vectors that will actually cover the input space. Now let's go through a bunch of